Hello, in this video I am going to show you how to build up a half-bridge converter, and first we will use this converter in DC-DC operation mode. We will have a DC link and then two switches. Once the upper switch is on, we will have a positive voltage in the terminal, output terminal, and when the lower switch is on, we will have a negative DC voltage here. Then we will have positive, negative based on which switch is on. We can have a DC or a bipolar DC here, which we can create AC voltage with this as well. So for the DC operation, if we calculate the average output voltage, it will be VDC over 2 times 2D minus 1, where D is our duty cycle. Now we are going to simulate this half-bridge converter using MATLAB simulink. We start from scratch, building a simulink model. A blank model. You can launch the library browser, and we will use simscape, electrical, and specialized power systems, fundamental blocks. We will use these libraries from the toolbox of simscape, electrical. I will add this to my model, power GUI, which is our solver for power electronics part. I will need a IGBT with a built-in diode, anti-parallel diode for my IGBT, and from passive elements I will take this as my series RLC branch as my load. Also I need a ground as a reference point, and I will need DC voltage source. So in the model you can just drag and drop them. Another way is to just search here. For example, I need another IGBT or diode, and it shows from which library you are taking this. And you can use Control R for rotation and Control I for mirroring. And if you right click and drag, hold right click, drag and drop, it will copy the components. I decrease it to, I'll just keep it 100 volts for now. This is my load. I am going to use a RL load, so I will change this to an RL branch. I'll leave these for the default values. This is my reference point, the middle one, from the DC side, and I will connect the converter. Here is my output. I need to measure its current measurement. Also, I would like to measure the voltage and voltage measurement block. So I will define this as my, we can use goto as our, to name our signals. I will name this one as IODM, detailed model, because later on I'm going to simulate the average value model of this converter. And I will name this one as BODM. Now I need to modulate this converter, turn the switches on and off. Also for settings, I'm going to simulate this converter 0.5 seconds. And you will right click, go to model configuration, you can use fixed, it's better to use fixed step size, and I will use 1e -5 for my as step size. And it's better to use discrete for power electronics. So solvers, I will use discrete solvers. Fixed step size, discrete, and I can change this one here to discrete. Again, I will use the same 1e -5, the same step size here in my power electronic solver. Now I have everything ready except for my switchings. I need to do switchings here. First, I will use a simple pulse generator. And I know these switches are complementary. One, when this switch is on, the lower switch is off, and once we turn on the lower switch, the upper switch should be off. Then I will use let me use the library to find a NOT block. We can use from, I think it should be in logical operator, which I can use and or not, or so I copied. Oh, I will add this to my model. And uses it as a NOT block. So then my lower switch will be complementary to my upper switch. And I will leave the amplitude 1. My period will be 1 over my frequency. And I'm going to choose 100 Hertz frequency for this. Pulse width I'm going to use for 50%. So half of for half cycle it will be on. For positive, the positive voltage will be here, and then negative VDC over 2 will be appeared here for the other half cycle. In total, my DC voltage, VDC, my DC link is 100 plus 100, so I will have 200 volts in VDC link, which is divided into half, 100 volts and 100 volts in series. So I will have VDC over 2 here. If I consider VDC as my pole-to-pole voltage from DC side, I will have VDC over 2 for half cycle and negative VDC over 2 for the other half cycle. Now I need to show my outputs. I will use a scope to show my output parameters, which is my current and voltage. Also, I'm going to call this one as my G1. You can do this to connect the signals to scope. When you bring it to the scope, it will change and you can connect it, or you can open up the scope, go to the settings, and number of inputs you can increase it to 3, and then connect the others if you want to show all of them in one scope. Then I need to save my simulation first before running. I am naming it half bridge example 1, and I will run the converter. Once your simulation is done, I would like to show them in separate figures. Now you do a auto scale and you zoom for a little bit to see a full period. This is 2 cycles, 1, 2, 3 cycles here. Let's look at one period here. For one period, when the switch, this is the upper switch, when in this period my upper switch is on, and for the half period my lower switch will be on in this part. So when my upper switch is on, I have plus 100 volts in the output terminal, and when my lower switch is on, I have negative 100 volts in my output. And this is my current rising during the positive cycle and getting down in the negative cycle. So what we do for converter control usually is the pulse width modulation. In order to do pulse width modulation, we usually compare a signal with a triangular wave, and then based on that we do the modulation. Now I would like to do the pulse modulation here. What I need is a triangular waveform. I will bring it from simscape. I believe we should have triangular waveforms here. For power electronics, in power electronics under pulse and signal generators here, you see a triangular generator here. I will add this to my model. Also, this PWM generator for multi-level inverters does the same, and here I have a PWM generator for two-level converter, which is, mine is a two-level converter. I have positive and negative VDC. It's two levels. I can just generate two levels. So I will keep this one for later. Control Shift X will comment this block in Simulink. And I'm going to use a pulse generator. And because I would like to see a DC voltage here, then before using this PWM mode, pulse width modulation, I would like to check another thing here. I will decrease the pulse width from 50% to 25%. So for 25%, my upper switch should be on, and for the rest, my lower switch should be on. Then I see that during one cycle from here to here, it's a one cycle. During one switching period, I have 25% of the cycle my upper switch is on and I have positive VDC here, and for 75% of the cycle I have a negative VDC here. And if you average this one, it will be VDC over 2 times 2D minus 1. It should be, and VDC over 2 times, because my D is 25%, 0.25. Then 2D minus 1 give me a negative value, negative half, times VDC over 2 should be 1/4 of VDC, negative 1/4 of VDC, which if you calculate the average in this square waveform, you can see that it is negative 1/4 of VDC, which comes to negative 25 volts. So we can confirm the theory with simulation, and I will now switch to doing the PWM now. I won't need this one. And I would like to, this is the modulation signal. As we discussed before in the class, we can use a modulation signal to generate the pulses, and we will compare the modulation signal with a triangular waveform to generate the pulses. Then we can, based on this M, here we will define M as our modulating signal. Based on the M indicates, we can see that our VO is directly related to M. VDC over 2 is a constant, and this M will define our VO. If M is a DC and constant value, then we will have a DC value in the output, and if M is a AC value, then if we give a AC signal, for example a sinusoidal signal, we will have an AC output. Then from DC-DC converter, half bridge will change to an inverter instead of using it as DC-DC. In DC-DC operation, we will have the inverter operation for half bridge converter. Now what I need to do is to compare my constant signal with my carrier signal, and I'm going to give, for example, 0 for this one. If you give 1, then for all the time upper switch should be on and lower switch should be off. Then we will have VDC over 2 here, VDC over 2 times M1, we will have VDC over 2, and if M is 0, as the first case I showed with the pulse generators, half of the cycle the upper switch should be on, half of the cycle the lower switch should be on, and then in total the average should be 0 here, 0 volts. VDC over 2 times M is 0, then we will have VDC 0 volts here in the output. Let's check if when we give 0, do we get 0 volts here? I need to compare these, so I'll go to, I need a logical operator. Oh no, this one, relational operator. And greater or equal to 0, then this is on G1, and its complementary should be G2. Okay, G1, G2. I will connect them to my switches. Okay. Now I will run the converter to see if I can see, and I changed my load to a resistor load to see it easily. So this is my output voltage. I can see that for half cycle it is 100 volts, and for the other half cycle it is negative 100 volts, and in total I should get an average of 0. For doing the average of your signal, you have two choices. You can use first order filter from specialized technology. This is one way to put a filter and see my frequency is 100 hertz. Right, 100 hertz. Or another way to get the average value is to use the mean from additional measurements, electrical specialized power systems. So I have my voltage here. The second one is its average from first order filter, and this one is the mean function. Again, I will increase to 100 volts, 100 hertz the frequency, and let me see if I can see 0 volts here. So the average is 0 volts, and if you take the average, you can increase the time constant to, for example, let me increase it 3 times, and I can see that this ripple will come down. You see this ripple of your filter will get down, and for this one so this ripple, again, if you take the average, we could see that because it's very low values, we will have a little bit ripples here, but the average is 0. And again we can see that our average is 0 here. So you have two different techniques to get the average value of your signal. I will go by filter and delete this one. For my future, I will name it go to, and I will name this one as my VO average DM. Now I would like to increase it to, for example, 0.5. I would like to show my average voltage too. So I can see that yes, for 0.5, again my DC voltage was 100 volts, so 0 times 0.5 should give me 50 volts in the average for my output voltage. Again, our simulation confirms our theory. In the next video, I am going to let's check if we give us before going to average value model. I would like to check again this sinusoidal signal as well. I will put a sine function here from the sources, and I would like this, as I told you, M is equivalent to our output voltage. So for the frequency, I would like to see a 60 Hertz frequency at the output. This frequency of your modulating signal is actually your output voltage frequency, and this one is the switching frequency. The carrier switching carrier frequency determines your switching frequency. And I'll again use the RL load. So run the converter, see the voltage. I can see that my output voltage average is a sinusoidal, and my current is almost sinusoidal. And here is my switching signal for first one, the upper switch. I would like to increase the switching 10 times. So from 100 Hertz I went to 1 kilohertz. And let's see what happens to my figures. I can see that by increasing the switching frequency, my figures gets more smooth, especially for the current. I will have more pulsations in my voltage, but the average still is a sinusoidal. Now in the next video I'm going to show how to build an average value model and compare the average value model with your detailed model.